Giant, covalency and carbon, GCSE, iGCSE and General Chemistry. Using chemistry explained in the correct way is crucial. Write notes and complete tasks either on paper or on tablet. You are in control of the pace. Replay the slides at a pace that is best for you. When prompted, pause the lesson. Think the problem through, taking your time and completing the task. Only when you are ready, continue correcting your work and then moving on. An overview of the lesson will start with the concept of giant covalent structures, look at two particular examples, diamond and graphite, move on to some carbon allotropes, fullerenes and nanotubes, and then a survey of nano properties. Check the specification that you are using or following, AQA, Edexcel, OCR A and B. A little care if you are following CIE, iGCSE. Some covalently bonded solids have very high melting points. So if we look at the three structural types that are associated with covalent bonding, we've got small covalent molecules, simple covalent molecules, polymers, and of course, giant covalent. How would you describe the melting points for small molecules and polymers, and what is the missing structural descriptor here? Pause, write down your ideas, come back when you are ready. Okay, to restart, small or simple molecular structures have low melting points, as do polymers, but covalently bonded substances with very high melting points have a giant covalent structure. Examples of giant covalent structures that you are expected to know about are diamond, graphite, and silicon dioxide. So let's consider silicon dioxide. Pause and write down the formula of silicon dioxide and suggest a type of bonding in the compound. Restart when you are ready. Okay, silicon dioxide, SiO2. We've got two nonmetals. So the type of bonding involved would be covalent. And we would expect silicon dioxide as a covalent substance to have a low melting point. But if you heat silicon dioxide, that is silica or sand, in a test tube over a hot Bunsen, you will find the solid will not melt. That means the structure of silica, silicon dioxide, cannot be simple small molecular or polymer structure. Those types of structures have low melting points. So it must follow that silicon dioxide has a giant covalent structure. Okay. Let's consider the bonding in silicon dioxide. Silicon has 4 outer shell electrons. It is in group 4 of the periodic table. That allows it to form a single bond with oxygen 4 times. So silicon achieves 2, 4, 6, 8, a noble gas structure. Oxygen, on the other hand, 2, 4, 6, 7, has not yet achieved that and is looking to form another covalent bond. It can achieve that by bonding to a second silicon. So each silicon is bonded to 4 oxygens, and each oxygen is bonded to 2 silicons. By that way, silicon achieves a noble gas structure, and so does oxygen. But that process continues and will continue forever. That is, it is a giant structure until the atoms run out. All of the atoms in a giant covalent structure are covalently bonded to other atoms. In melting, these covalent bonds, which are strong, must be broken. And therefore, the melting point of covalent giant structures is very high. The 2 other examples mentioned earlier in the lesson were, of course, diamond and graphite. Now, both of these are forms of carbon, and both have very high melting points. Here is a structure that you may have seen before. Pause. Is that diamond or graphite? You are expected to recognize. Have a guess. Come back. Okay, so this is a structure of diamond. And on the right here, we have the structure of graphite. Both are giant structures. Both have high melting points. Both are giant covalent structures. We'll go through the detailed chemistry of that in the next section. So let's do that. Diamond and graphite. Diamond and graphite are both forms of elemental carbon. The atomic number of carbon is 6. Pause and write the electron arrangement for the carbon atom. Okay, so the electron structure for the carbon atom is, of course, 2 in the first shell, 4 in the second. So carbon atoms have 4 electrons in their outer shells. So these are the electrons involved in bonding. Of course, carbon will bond covalently with other carbon atoms. Carbon is a non-metal. Carbon-carbon combination is non-metal, so that would imply covalency. Covalent bond, of course, is a shared pair of electrons. So here is a carbon atom covalently bonding to a second carbon atom. So just as with the previous example of silicon, single bonding between carbon atoms will result in a giant structure in that a central carbon will bond to 4 carbons, forming 4 shared pairs of electrons. And then if I take this carbon at 9 o'clock to be an example, this carbon has 1, 2, 3 unbonded electrons available to make 3 further covalent bonds. So each carbon will look like the central carbon with 1, 2, 3, 4 covalent bonds to other carbons. And that structure will continue until you run out of carbon atoms. So let's take diamond as the first giant structure of carbon as an element to consider. As we saw, each carbon atom can form 4 covalent bonds to achieve a noble gas structure. And we're suggesting in the giant structures such as diamond, each carbon forms single bonds to further carbons. If we extend that structure, we will get a giant structure. This carbon here I'm highlighting needs to form 3 more covalent bonds. So if we take here 1, 2, 3, 4, each carbon in the structure has 4 covalent bonds. And that structure will continue until we run out of carbon atoms. But what are the properties of diamond? You are expected to recall some typical properties of diamond. Pause and write some down. Okay, so the typical properties of diamond would be high melting point and hardness, and also electrical non-conduction. Again, what is the explanation for these properties? Pause and write some explanations. Come back to check when you have done so. Okay, so the explanation revolves around each carbon having 4 covalent bonds, but that those covalent bonds are all strong. High melting and hardness, high melting point and hardness, both involve the idea of resistance to breaking. Diamond has a high melting point because the bonds are resistant to being broken. Diamond is hard because the bonds are resistant to being broken. They are strong. Electrical non-conductance, well, that's to do with there being no free or mobile or delocalized electrons or ions. There are no charged particles in this structure. These are atoms covalently bonded. So there's no free electrons or ions. Now let's talk about graphite. Here is the structure I showed you earlier. How many bonds does each carbon have? Look at the central carbons and not the ones on the edges of the diagram. And what shape do the carbons adopt? Pause, write down your answers. Okay, so I hope you can see that the carbons arrange themselves into hexagons, and that those hexagons form parallel layers. Each carbon, 1, 2, 3. This carbon I'm highlighting, 1, 2, 3. Each carbon forms covalent bonds with 3 other carbons. So that means that there is one outer shell electron that is unbonded. So each carbon, if I show this as a dot, has one electron that is not involved in forming a covalent bond. There, if you recall, there are 4 electrons in the outer shell of carbon. If carbon only forms 3 covalent bonds, 1, 2, 3, then there is 1 unbonded electron on each carbon. And you will recall from metal structures the concept of delocalized. Those electrons are able to move anywhere throughout that parallel layer of hexagons of carbons. So we say that the electrons here are delocalized. You'll also notice that there are no covalent bonds between the layers. The covalent bonding involves the carbons in the hexagons in the layers. The distances between the parallel layers of hexagons are much greater, and there are no covalent bonds between the layers. What do you know of the properties of graphite? Pause and write down what you know at the moment. Come back when you're ready. Okay, so graphite has a high melting point. Graphite is soft. It's the material that principally makes up pencil lead. It's slippery. It is a conductor of electricity. Pause. Can you explain those properties? Write a statement for each. Come back to compare to mine. Okay. So obviously high melting point. We've got a giant structure that contains strong covalent bonds. What about soft and slippery? Well, the layers can slide over each other. With ease. There are no covalent bonds between the layers, so the layers can slide left or right without there being an energy barrier. Conduction. The delocalized electrons move throughout the structure. And of course, they carry charge. So there are our explanations, or the standard explanations, for the properties of graphite. High melting point, well, it's a giant structure of strong covalent bonds. Why is it at the same time soft and slippery? Well, there are no bonds, no covalent bonds between the layers. Just, if you recall the concept, weak intermolecular forces. So the layers of carbon hexagons can slide over each other. Why is it an electrical conductor? Well, just like metals, we've got an electron that becomes delocalized in the layer and can move throughout the structure and carry charge. Fullerenes and nanotubes. Fullerenes and nanotubes. Now, fullerenes are molecules of carbon atoms with hollow shapes. The most famous was the first discovered Buckminster fullerene, which is a molecule with 60 carbon atoms. So again, it's elemental carbon. And here is a model of Buckminster fullerene. Look at it carefully. What are the shapes that you can see inside that Buckminster fullerene model? Pause, come back when you have your answers. Okay, so we can see rings of 5 and of 6 carbon atoms. 1, 2, 3, 4, 5, a pentagon. And just to the left, 1, 2, 3, 4, 5, 6, a hexagon. So rings of 5 and 6 carbon atoms. These are arranged to form a structure that's very similar to the panels of a modern football, and therefore picked up the nickname a buckyball due to this spherical shape. The uses, this is a relatively new material. Transportation of drugs in the body. A small molecule can be placed inside a buckyball, and the buckyball can transfer it to the required organ. Catalysis, again, a metal ion inside the buckyball can be taken to a reaction site. So Another relatively new material are carbon nanotubes, which are simply cylindrical fullerenes. So here is a model that you may have seen in your school classroom. Here's an image, artist impression. So this is a closed fullerene. This is an open cylindrical fullerene. So this is a nanotube. This is perhaps a fullerene, but it's tubular. The advantages are, of course, a very high length to diameter ratio. So these nanotubes can be extremely long. First time I heard of nanotubes, the lecturer had some ideas for their uses, such as a 2-mile long fishing rod. And of course, because all of these bonds are carbon-carbon covalent bonds, the bonds are very strong. So even if there are only small proportions of nanotubes, carbon nanotubes within a substance, that will have a considerable strengthening effect on the material. But these nanotubes may also be electrically conductive, and therefore they have just found uses in modern electronics. Another modern material is graphene, which is a single planar layer of carbon hexagons, so as it were a single layer of graphite. Of course, that means we've got hexagonal rings. What does that mean in terms of electrons? Pause, see if you can recall, write down some statements. Okay, so each carbon is bonded to 3 others. So if we take this carbon here, 1, 2, 3. Each carbon is bonded to 3 carbons, which means, of course, that the 4th electron of the outer shell is not bonded and is delocalized through the layer. So those 4th outer shell electrons, 1 from each carbon, is able to move anywhere throughout that structure. Can you predict the properties of graphene? Okay, so you've made your predictions. It's going to be strong. These are all strong covalent bonds, and all of the carbon atoms are covalently bonded to 3 other carbons. So a large amount of energy needed to break those bonds. There's going to be resistance to breaking. And graphene is an electrical conductor along the layer. So this is a modern material that is now increasingly used in electronic devices. I'd like to finish the lesson with some review problems, which just relate diamond and graphite to some potential uses. Which of the models A and B, so model A, model B, represents diamond and which graphite? Which substance, A or B, has the following use: as a lubricant, as an electrode, as an industrial cutting tool? Pause. You've got 4 questions to answer. Write your answers down. Come back to check against mine. Okay, so which is diamond, which is graphite? Well, this is obviously diamond on the left, I say obviously you have to recall, you need to recognize that structure as being carbon bonded to 4 other carbons. That's the telltale characteristic. Whereas if we look at this structure B, 1, 2, 3 carbon bonded to 3 others, forming hexagons in parallel layers, that of course is graphite. Which substances have the following uses? Well, as a lubricant, graphite is used as a lubricant. These layers can slide over each other. Machine parts coated in graphite can move past each other smoothly. Graphite is an electrical conductor. The carbon rods that you will meet in the school laboratory, they have a high graphite content, so they are electrical conductors, suitable as an electrode, so that again would be graphite. What's distinctive of diamond is, of course, its extreme hardness. Graphite, if you recall, is soft and slippery, hence it is a lubricant. Graphite is an electrical conductor, hence it is suitable for an electrode. Diamond is strong and very hard, so it's used as an industrial cutting tool. So you now need to practice. I suggest you first of all do the textbook end of chapter questions, for which you probably can find answers, and then move on to past paper questions from the particular exam board that you are taking. If you don't have immediate access to those, there's a website, Maths and Physics Tutor, which has collections of past papers and answers by exam board.